So we've played some days now with how bodies are moving. They can move in a constant change of position with time, every 5 feet every second. They can change with an increasing amount of distance they cover in that same amount of time, and that's acceleration. They can also lose some amount of ground that they cover with time, and that's deceleration. But we haven't talked a little bit now about what causes that. What is the change caused by? And it's related by the same person who studied both of these effects. What I'd like to talk about today are forces. And a force is nothing more than a push or a pull, and it's given in a certain direction. So just like acceleration and velocity are in a certain direction, they're vectors. And we'll continue to work with them and get used to them as far as we do projects and try to grow in our familiarity with working with them. Some of those yesterday may have been a little bit more of a challenge, that last set of problems, but I want you to sort of stretch yourself to give those a try, to learn those as we go. So what that force is going to be measured in is newtons. That was after the Isaac Newton sort of work that's there. He was actually on a school break. There was an outbreak of plague, and he had gone to his aunt's farm, Isaac Newton had, and it wasn't that the apple fell on his head, but he would think about how things moved and stars at night, compare those to things that were falling in the earth, and he was trying to put them all in together. Now, those forces that Newton talked about, just to give you a feeling of those, this is a 100-gram weight, a 1/10 of a kilogram. You can see it's not very big. It would be maybe the size of a bigger watch that you might wear, but that's a 1 Newton force. Okay, maybe the weight of your clothes is about a 10 Newton force. Okay, this is also a 10 Newton force here. It's a 1 kilogram mass. Okay, that you would be able to hold up about 2.2 pounds of material. That force is there. 1,000 Newton force is somebody like me who weighs about 100 kilograms. It's 1,000 Newton force to stand the ground. And then, alas, of course, 10,000 newtons. Just so you get a feeling for those, when we talk about how much force is there, is the weight of a car. Small car, probably. But all of those are forces that maybe you can relate to and then put those in your mind in some way. What I want to talk about is where do those come from? And there are 4 places in nature that exert forces. One is an attraction between any masses. I mean, even the person sitting next to you is exerting a small but gravitational force. Usually these are between all sorts of matter, and they exist at all distances. It gets weaker as you get further from each other in gravity, but it is the defining sort of structure-making process and force in the universe. There's an electric force, and that's that effect of having either 2 negatives being repelled by each other, like the electrons around an atom are a positive and a negative, where the atom actually holds the electrons into each other. But the electric force is almost all of the forces that you know. If somebody comes to push you, it's because those electrons in their fingers are actually getting repelled against this outer skin of yours. They're pushing against you. Okay, so that is actually from electric force, that contact we make just with our hands or to pull on things. These two are happening only in the nucleus. The strong force actually holds the protons that are positively charged next to each other. There's an advantage to sticking together in groups in these bigger atoms, and that's because the strong force is involved. And as soon as you get that too big, when those atoms get to be really big, that strong force can't hold together these massive atoms, and they fly apart as the protons take over, and that plus charge causes them to break apart and fission. The weak force actually happens inside even those smallest particles, the neutrons, and they govern whether a radioactive decay can happen or not. So those 4 forces are the only forces that we have known in nature, and they govern most of those, although I would say almost all of ours in the natural sort of process is occurring under the electric force. Now, Newton, while he was describing his laws and thinking about those, didn't know anything about these 4 forces of nature, and they came only more recently, probably in the late 1800s through the early 1900s, 1930s, 40s. But he did describe the way mass is going to act. And I've put a couple of things that I think I can relate to just growing up in the sort of Midwest here, is that, one, there is a body that can stand and it won't move, or it will stand without motion. And that doesn't mean that there aren't forces on it, but it just says that there's a balanced set of forces on a body causes no change. Now, you may not be able to see this. I'll just come over, and these are the small radio telescopes, not telescopes, radio towers. Here, let's come down so you can see them. That are held up by many different forces holding them in place. That's a lot of weight that's typically at the edge. You can see this is the one that's a little closer. That's what they use to broadcast radio signals. And that is not moving, but there's lots of forces, but they're all balanced and it's holding that thing in place. So a body in rest stays at rest, and a body in motion then would stay in motion is what basically Newton was saying. Now, one of those tendencies for that body at rest or any kind of a body to resist the change of motion is actually well distributed or described here. If I watch a rodeo clown, for instance, that's coming in, is that the smaller mass actually is easier to move. It's got less inertia to the clown's advantage to get around in a rodeo around the sides of the bull, and he can stay away from him because he can make quicker changes in directions. Trouble with that, though, is that a body in motion can continue to stay in motion, and if he isn't careful, he can gain some of that net force. And that actually goes to then describing our second law, is that if a force is applied to some body, okay, some mass, your body, a car or whatever, then that mass will gain an acceleration, like this poor gentleman has experienced after being forced by the bull. So those are a second law that governs all acceleration we've talked about in those movement equations we've been doing is going to be caused by a force. So if you know what that force is, and you know how big that object is, the mass of that object, you can then tell what the acceleration is and still continue to use those equations we've talked about in terms of movement. Okay, the last of these forces is going to be called the action-reaction force. So here's the force is causing mass to excel. This is the second law, but the third law is that there's always two forces that are acting in between things. And that is, if I'm pushing on something, that same something is pushing back on me. Now, they always exist between the same two objects. So if I was to push on this wall, it's the force of the wall pushing back on me and driving me away. If this was a slick, icy floor and I pushed on this wall, that wall would push back on me and I'd start to slip away from the wall. You'd notice that if you were in a boat, for instance, and you were going to run across and jump out of the boat and onto the shore, the boat responds, you're pushing on the boat to move you forward, and the boat pushes back, and it moves backward. So between the two of you, you both are being pushed away from each other, but the boat pushes on you as you are pushing on the boat to hopefully land somewhere else. So those are the basic sort of tenets that you're going to see, forces at rest or at causing motion. And I want you to answer a few questions on the sheet today here for that.